All right, today's topic is really important, hash functions. But of course, our focus is in lightweight cryptography. So at the end, I will also talk about lightweight hash standards, different designs, and so on. So let's start with what a cryptographic hash function is, and then see how we can use it in practice. So definition is simple. A hash function h is a keyless algorithm that takes a variable length input x and returns an output y of fixed length n. And here we call the n the message digest, and the size of this output is called the message digest length. Okay, so why is the message digest? So as you can see, the input is of variable length. So here actually you have a kind of a infinite space, but the output space is fixed, and it is fixed to the length n. So in practice, in the past, n was small, like 128 bits, but today we generally prefer 256 as the smallest n, and you can choose 512 and so on. So this is a basic definition for hash function, but for a cryptographic hash function, I want more properties from such a definition. Okay, so we expect a cryptographic hash function to satisfy the following properties: premise resistance, second premise resistance, and collision resistance. So I will explain them one by one in a minute. But at the end of the day, what we really want is that a hash function to behave like a random function. So the output should appear like a random zeros and ones. And actually, this idea is used in cryptocurrency mining anyway. But that is another topic for another day. Okay. So let's start with the first property that I would like to have. This is called premise resistance. So you have a hash function h, and I'm giving you an output of this function. So for this output, it should be hard for you to find an input x such that hx equals to y. So this is actually why we call these functions a one-way function. So when you have the input, you know the algorithm, it is easy to calculate output. So in one way, it is easy, but the other way around, it should be hard. So by hard, we mean the following. A generic attack will require around 2 to the n operations. Since the n is the size of the output y, if you put 2 to the n different input to this function, at some point, most probably you will hit this value y. Okay, this is why a generic attack would require 2 to the n operations. Why would we need such a thing? For instance, here is a basic scenario where you can use it. In the past, people stored username and passwords as plain text in a text file in a database where they store it, but they stored it as plain text. But these files or databases leaked in the past. So when this happens, people's password also leak, and people use the same password in different accounts. So this way, a lot of problem occurs. So easiest thing you could do was to, instead of storing the hash, instead of storing the password in the database, simply store hash of the password, right? A basic solution, because this is sufficient to verify a password, because whenever you want to log in, you will provide the password, the server will calculate hash of the password and check if the hash matches the one they stored. So it is enough to verify. An attacker that captures the password file has to find the preimage. So knowing the hash from here to going back to password, as we said, is the premise resistance, right? But of course, if your password is really easy to guess or short, then the attacker can perform a brute force attack. So in practice, this example I give you is not enough. What we do is generally concatenate a random value that is called sol to the end of your password, then calculate this hash. And to slow down the attacker's efforts on a brute force attack, instead of storing the hash of this password concatenated with hash, you calculate the hash of it recursively, like thousands of times, so that this way it will be harder for the attacker. So instead of a single hash, you perform the hash function like 10,000 times or more. Okay, depends on your choice. So this way, if you keep only a single hash value, then for instance, maybe the attacker has a lot of computational power and capture the password in one day, right? So if you hash it like 1,000 times, then that one day turns into 1,000 day. Okay. Let's move on to the second property, second primary resistance. So given an output y and an input x1 such that hx1 equals to y, it should be hard to find any other input x2 such that hx2 equals to y. So this is why we call it the second primary resistance, because we already know an pre-image x1 that gives this output. Now your aim is to find a second one. Of course, x2 should be different than x1. Okay. Again, a generic attack will require around 2 to the n operations, but if there is a weakness in this design, you could find such a pre-image by performing less than 2 to the n operations. So how can this may come in handy? First, you store the hashes of all of your files in your computer, okay, and store it in a secure list someplace. So if the attacker modifies the files, for instance, put a malicious code inside them, and if you calculate the hash of this modified file, it wouldn't match with the previous one. But if the hash function is bad and it allows second pre-images, then the attacker can put a malicious code and still provide the same hash value, and this way the attacker can fool you. Okay, this is just a basic example, but we need second pre-image resistance in many different scenarios, especially when you're signing something digitally. Third property that we want is collision resistance. So it should be hard to find two inputs, x1 and x2, such that hx1 equals to hx2 equals to some value y. So this looks very similar to the previous one. So the obvious question to ask, what is the difference? So in the previous definition, the x1 was fixed, so you don't have any control over x1. Okay, so you are given x1, so you are given y, you are trying to find x2. Here I'm giving you more freedom. I'm telling you that this is a hash function. Just try to find two input that gives the same output. Okay, you have the whole freedom in choosing x1 and x2. So for this kind of, in this scenario you have more freedom, a generic attack will require around 2 to the n over 2 operations. As you can see, this is square root of the previous generic attack. So this is really small compared to them. For instance, if n is 256 bits, here you need 2 to the 256 operations to find a pre-image or second pre-image. Here you need the square root of it, which is 2 to the 128 operations. This is due to birthday paradox, which I will explain in a minute. Okay, so why do we need such a resistance? Actually, an example is as follows. Assume that hacker prepares two versions of a software driver for an operating system, where X1 is the correct version, which doesn't have a malicious code in it. And also, the hacker also provides the same software driver, but this time it contains a backdoor or a virus in it. So, but both of them have the same hash value. Hacker sends X1 to the operating system company for inspection, for instance, Microsoft. Microsoft checks that there's no problem in it, so it's secure. So they sign it, but they don't sign the whole driver, because nowadays, drivers can be a few hundred megabytes. Some display drivers now are around 3 gigabytes and so on. So instead of signing such a thing, the operating system company actually signs the hash of this driver, okay? So which is very small, something like 256 bits. So you sign this with, for instance, Microsoft signs it with their private key. But hacker distributes x2 instead of x1, and x2 contains viruses. But the hash of x2 also equals to x1. So when you try to install this, operating system checks if it has a valid signature, and it has. So this way, operating system would not tell anything to you saying that this has a problem, because this signature works because hx1 equals to hx2. Okay. So we need all of these properties in practice. And before moving on, let's talk about birthday paradox and why this is easier to find collision than a second pre-image resistance. Okay, and it is way easier because the square root actually reduces the number in a really fast way, right? So what is the birthday paradox? Question is as follows: how many people need to be in a room before it is more likely than not at least two people share a birthday? Okay, so by more likely than not, we mean with probability more than 1 over 2. So think about it in this way. One person enters a room. Initially, it is empty. Since there's only one person in the room, they don't share their birthday with anybody else in the room. But when the second person comes, there's a very small probability that they have the same birthday, right? But of course, most probably they don't. So you put the third person, fourth person. So question is, at which point the probability will be more than 1/2, so that there are two people in the room that they share the birthday, okay? So when people is asked this question, they generally say the half of the days in a year, like 180 or something, okay? It feels like this is the correct answer, but the correct answer is 23, which is very small than 180, right? So this is why we call it a paradox, okay? Especially there's nothing surprising about it, because I will show you how to calculate it in a minute, okay? So consider the probability that nobody shares a birthday. The first person in the group has birthday on a given day and they don't share it with anybody, so this has probability 1. You put the second person in the room. So in order for them to not share the birthday, the second person should have a different birthday than this one. And you subtract 1 day from the year. Third person shouldn't share their birthday with this person and this person, so you have to multiply this. So when there are 3 people in the room, this is the probability that none of them shares a birthday, okay? Right? So probability that they share a birthday is 1 minus this value. So question is, when 1 minus this value exceeds 1/2, right? So the probability P that we have at this one match is 1 minus the previous multiplication, which is this, okay? Calculation shows that we have this probability is larger than 1/2 when T equals to 23, okay? So when there are 23 people in the room, the probability is around 0.507, okay? More than 50%. But this, by the way, this probability increases drastically. So if there are like 35 people in the room, most probably 2 of them share the birthday. So you can try this in any seminar, okay? If there are more than like 23 people, you can give it a shot and it works. For the more general case where we have T people and n possible birthdays, it can be shown that this probability equals to approximately 1 minus this value. So when there are n possibilities, after making approximately T equals to the square root of n choices, we have a collision. This is why when we talk about here, by collision, we mean they share their birthdays. But if we go back to our collision resistance, here the output size is n bit. So assume that there's a planet where there are 2 to the n days in a year, okay? So question is, how many people you need for them to share a birthday? The square root of it is the answer. Of course, there's a constant in front of it, but since the number is really large, we don't actually deal with this, okay? So this is why it is easier to find collisions. So this is why actually the choice of n depends on this value. Because in the past, n was chosen as 128, like in the case of MD4 and MD5. But this would require 2 to the 64 operations to find a collision. And 20 years ago, it was hard to perform 2 to the 64 operations due to our computational power. But today it is not a problem. So this is why n is increased today. Like in SHA-2, we choose n as 256 generally, okay? All right, let me show just a few use cases. Why would I need such a compression function? Actually, hash function kind of reduces everything into like 256 bits or something. So just think about very different use cases just that came up to my mind. A forensic investigator would like to have a very small digital fingerprint of every storage device at a crime scene to detect if any modification to these devices happen in the future. And actually, this is what legally they do. So at a crime scene, if you find any hard drive, anything that stores data, you actually have to calculate the hash of it and record it in the document, so that if in the future during the investigation, if somebody maliciously puts something in the drive or deletes something, you can say that the hashes do not match. So you say that it was tampered. So it actually checks the integrity of the device. Also, let's say that you copied a lot of files in your computer to different folders, and now you want to really find duplicate files. Easiest thing I mean, not the easiest thing, but one thing you can do is to calculate hashes of all of your files, okay? Then sort them. If there are two files with the same hash value, the hash values will collide, and this way you can detect the duplicate files, okay? Another solution, actually, this is how cloud works, by the way. Millions of users upload the same file to cloud, like for instance, Dropbox or Google Drive. But cloud provider wants to store only a single copy, right? Why would they waste space when they have the same file many times? And therefore, they only store one of them. So whenever you want to upload a file to Dropbox, actually Dropbox first check on your computer if it is already in their storage. So for instance, if I upload an image to Dropbox, and 1 hour later, if you put the same file to your Dropbox folder, Dropbox detects that they already have this file and tell you, okay, don't send it to me, I already have it. So this also saves you the bandwidth, right? You don't transfer the file over and over again. And this is important. If you don't use this, then Dropbox have to pay a lot of money to buy more hard drives so that they can store all of the files of every people. Another example is that an intelligence agency wants to give a list of illegal files to forensic investigators without sharing the files themselves. So you know that there are some illegal files, and and in child pornography, this is the case. Instead of sharing these files, you simply calculate the hash of this, and you actually give them to, forensic investigators, but also to cloud service providers. For instance, Apple Drive, Google Drive, they already have a list of files, which are, in this case, illegal files, but also they can be copyrighted files. So just, for instance, download the copyrighted files and try to put it into your Dropbox folder, and Dropbox will reject to store it. So they will say that this is an illegal or copyrighted material. And they will say this because they will just look at the hash of your file, and they will check if that hash is in their list of illegal files, like a blacklist, right? So of course, this only works if you already know an image is illegal or a file is illegal. Another thing is that this time a forensic investigator wants to check if a disk contains any illegal file that are pre-obtained, but you simply check the hashes of the files in the drive and check if it is in the blacklist, and so on and so forth. You can give many examples here, okay? And you can create many Kickstart companies just using these properties, okay? Of course, these were just for generic daily use, but in cryptography, we use also hash functions in many different scenarios, and this is why we call it the Swiss Army knife of cryptography. So hash functions have many uses in cryptography and considered the Swiss Army knife of cryptography. Some of them are digital signatures, message authentication calls, pseudo-random number generators, key derivation functions, and so on. So we use hash functions almost everywhere. So for instance, in digital signatures, you never sign the message itself, you sign the hash of it. Okay? This is the idea. Also, in cryptocurrencies, everything hashed. So. And by the way, hashing is not encryption, okay? This is important. Here, I'm not providing any confidentiality. I'm actually solving the problem of integrity. This is one-way function. And encryption is two-way function. You encrypt and then decrypt back, right? If I cannot bring the data back, then I wouldn't call it an encryption. Okay? This is really important. And especially in blockchains, the security comes from hash functions because you are chaining the blocks by calculating their hashes.